Hey everyone, in this video, let's take a look at question 377, combination sum 4 on Leetcode. This is part of our blind 75 list of questions, so let's begin. In this question, we're given an array of distinct integers called nums and a target integer called target, and we want to return the number of possible combinations that add up to target. For example, if you have the nums 1, 2, 3 and a target of 4, we can see that there are a total of 7 combinations that add up to target, and notice here that different sequences are counted as different combinations. For example, the sequence 112 and 211, they're technically the same combination, but here we're counting them as separate. And for example, if we can't form the combination so that adds up to target, we just return 0. We've done a question like this before, right? We've done the question combination sum. So in this question, let me go ahead and actually might already have, I already have the stuff copied and pasted in. So let me just go ahead and do that here. But what did we do in combination sum? In combination sum, essentially the question was we wanted to find combinations such that they add up to target. So if you think about it, what we could do is we could basically just use combination sum, and we can start off with that. One possible way is that we can just take this list that's returned and we just return the length of it, right? We just return the length of it because that's what we want. So maybe we can start off with that to see if we can arrive at the solution. But before that, let me just quickly go ahead and explain my solution as to how I did combination sum. And if you want to learn more in depth, you can watch the video. But basically, for combination sum, we started off with a backtracking type approach. And we always have this kind of format for a backtracking type questions. So what did I do? Well, I have my result variable where I stored my ending list of combinations that add up to my target. Then here I have 0, which is like my initial index that I start off with. I also have 0, which is my initial sum. And then what I basically check is if my total sum is equal to my target, then I go ahead and append my current list, which basically I use to store all of my values. I append that to my master list, and then I return. Otherwise, I go through the loop, and then I first of all check to see if I can add this current number into my list, because if it's less than target, only then I can add it. Less than or equal to target, only then I can add it. And if I can add it, then I go ahead and add it. I update my total sum, and then I go ahead and pop it at the end. Now, there's two things here that we can actually improve on. First of all, we want to return the length of res here. Instead of just res, we want to return the length of res. And other thing you might notice here is that I'm actually going from index I, and then when I'm doing my loop, I'm actually restarting at index I. And this was because we could use the same element again and again. But notice that if we do this, we actually won't have combinations that are duplicates. For example, if I go ahead and try to run this on my sample test cases 1, 2, 3, and 4, you can see that our answer will actually be 4 instead of 7. The reason we're not getting 7 is because we're not considering duplicate values. So what I mean here is if I go ahead and I print out res, you can notice that when I print out res, let's see what I get. Well, I get 1111, I get 112, I get 13, and I get 22. But notice how I don't get 211, which is basically another combination that's in the past. Notice I also don't get, actually, the reason I don't get 211 is because it's a repeat of this, right? It's because of, it's 211, it's a repeat of this one. And similarly, like 3 and 1 and 1 and 3, I don't get 3 and 1 because it's a repeat of this. So it's very easy to fix that. Basically, we'll just turn this into a 0, which means that when we are recursing, then we'll go back to the 0th index instead of the current index. So if I go ahead and submit this, then you can see that this is actually a working solution. It's obviously not good because we're generating the entire list, but at least we can start off with that to see where we are. And again, if you want to learn like how exactly we went about generating this list, solving this method here, then go ahead and check out the combination sum video, and that should help out. But basically, how can we fix this, or like how can we make it better? Well, one thing we can do is like we don't need to generate the list, right? How about we change this problem so that maybe what we can do is we can have our answer as 0. We'll return our answer in the end, and then maybe something we could do is if my total sum equals target, let's just return a 1 to indicate that okay, we've been able to form like one combination that adds up to target, and then we don't actually need to add on to cur here. And so what we can do is we can add on to answer here, and here we can just go ahead and return this here, right? So now what I did is I transformed my solution here into one in which I don't actually add on to cur, but I'm just keeping track of the total number of combinations. You can see if I form a combination, I return 1, and then in my loop, I basically just go ahead and add on the remaining amount of combinations I can form, and I return that at the very end. Now you can see that instead of a memory limit exceeded, we get a time limit exceeded error here. So the reason we get this is because we're doing a lot of recursive calls, and so we can actually cache our information. So how can we do that? Well, before we go ahead and cache it, let's see if we can clean this up a little, because we have a lot of variables here that we don't actually need. For example, this res and cur, this is actually not needed at all. So I can remove res, I can remove cur. This index, technically I don't need it because I'm just starting off at 0, but let me just go ahead and keep it here. Okay, so I'll remove res, I'll remove cur. Now, what else don't I need? I can remove res from up here. Okay, now what else don't I need? Well, we have this total sum plus nums at I, right? This total sum, if you think about it, do we really need this? Well, we don't actually need it, right? Because if you think about it, we can just use the target variable. This target variable, it starts off at a value that's greater than 0, right? So I think we have the condition. Target value starts off at value, minimum as 1. So basically, whenever we want to add on to target, why don't we just remove from target? So maybe we can do something like this. Maybe we can do target minus nums at I. And so then how do we know we arrived at a solution? Well, if target is equal to 0, then we know we arrived at a solution. So it's just a different way of thinking about the same thing. Now, we have to change this, right? How can we change this? Well, what we can do is we can do if target plus, or I guess if target minus nums at I, if this is greater or equal to 0, then we know we can consider it, right? So this is just another way of thinking about it. So in that case, we actually don't need total sum either. So I will go ahead and remove total sum. Now let's see if we can go ahead and submit this. So obviously this will still get a time limit exceeded error, but I'm just making sure that my code still works here. It looks like it still works. We'll just get a TLE here. So how can we further improve this? Well, in order to further improve this, we need to introduce memoization. That's how we improve these recursive type algorithms. So let's go ahead and do that. And we already know how to do that. So I will create my memo, which is a dictionary here. And I will create my memo over here. Now, what do I need to memorize? What do I need to cache? Well, what is changing here? Only one thing is changing, right? This target is changing. So all we need to do is cache this information here. So how can I do that? Well, I can do something like, before I return, I will do memo at target is equal to answer. And then I can actually just check. I can check if target in memo, then I return memo at target. And so that's my memoization approach. So let's go ahead and see if this works. So this should drastically speed up our recursive algorithm. And you can see it does. So we're actually pretty fast right now. Now, we can actually take this one step further and do dynamic programming. So we don't actually have to do recursion at all. And the way we do dynamic programming is we can take a look at what exactly we're memoizing and convert that into a dynamic programming array. So let's take a look at that. Let's take a look at what we're doing here. Okay, so in dynamic programming, we want to create an array. And what exactly are we caching here? Well, we're caching the target, right? And we notice that the target, the maximum value of the target is target, and the minimum value is 0, right? So we can actually just create a dynamic programming array where we do something like this. So what am I doing here? Target plus 1. Essentially here, let's say target is something like 3, right? Target is something like 3. Here I'm creating a dynamic programming array where initially we have zeros everywhere. So what do these zeros kind of represent? What does this represent? Well, this kind of represents the amount of ways we can form the 0 sum. This represents the amount of ways we can form the 1 sum, the 2 sum, the 3 sum. So kind of this is what it represents here. Now, if you think about this, what is the amount of ways we can form like the 0 sum, right? Like what is the amount of ways we can form just 0? Well, just 1, right? We don't take anything that will form the 0 sum. So we already have one base case. So dp at 0 is equal to 1. All right, so we have that. So now if you think about it, what I'm basically doing is I basically want to figure out like how many ways can I form the sum 1? How many ways can I form the sum 2, the sum 3? And in the very end, I can just return how many ways I can form the sum 3. So instead of this, I will just return dp at target in the very end. Okay, so now we have our dp array. We have what we want to return. Now let's go ahead and we do a recursion here. Or not a recursion, our for loop, which is basically identical to this one here. So what will I do? Well, I need to go through my dp array, right? I need to figure out how many ways can I form the sum 1, form the sum 2, and form the sum 3. So how can I do that? Well, I can do for I in range. And notice how I'm already filled out dp at 0. So I can start off at 1, and then I can go till the length of the dp, right? So now let's assume let's assume that our values are bigger, right? Let's assume that we have something like this, dp 4, 5, 6, and 7, and let's assume that I this pointer here, I, is over here. So we want to know the amount of ways in which we can form the sum of 4. We want to know the amount of ways we can form the sum of 4. Well, how can I form the sum of 4? Well, I will just copy what I have here, right? If you think about it, we can just copy what I have here. Now, what is target up here? Target up here is basically I, right? Because I want to form target of 4. I want to figure out how many ways I can form this 4 over here. Okay, so we have that information. So what are we doing? Well, if you can see here, we're basically just going through the numbers and we're seeing which one of them I can use to form the target of 4. So I can use a similar approach here. What I can do is I can do for num in nums, what can I do now? Well, for num in nums, what am I doing? Well, I want to basically figure out if there's a way, and actually maybe we can just follow exactly. How about we just follow the same approach here? For j in range, 0 to length of nums, right? So j here, or I guess j here corresponds to like a number, right? J here corresponds to a number, so corresponds to number, right? Corresponds to a number here. Now, what are we doing? Well, we want to basically figure out that can I use j to form my target I? Like how many of these can I use to form my target I? So what can I check? Well, I can check. What can I check? I can check if first of all, if target, which is if I minus nums at j, right? If I minus nums at j, which is my number here, and I is my target here, if I minus nums at j is greater or equal to 0, well then I can use this number, right? I can use the number at like index j. So what can I do here? Well, I want to basically increase my answer, and increasing my answer basically means increasing my dp value. So I can do is dp at target plus equals what? Well, what's changing here? It's just this value here, right? Target minus nums at I. So this will be plus equals dp at target minus, not nums at I, but nums at j, because here we're using j to coordinate our target. And basically here, target is just I, but to kind of just follow what we did here, I'll just use this approach. And so this is all we need to do in this approach. So let's go ahead and run our code to see if we pass. Okay, let's go ahead and maybe try a failure test case like this time limit exceeded one to see if we pass here. Okay, and let's go ahead and submit. And so we should see that this solution ends up working. And so what is the time complexity of this one? Well, it would just be the time complexity of, well, we have to go through the length of the DP, right? So that's target, so length of target, so just target, like target, and then times the length of numbers. So that would be the time complexity. And the space complexity is actually just whatever the size of the target is, because that's what we store in the DP array here. So again, let's just go through this again to kind of see like how we transition from a recursive algorithm to a dynamic programming one. Well, here we understood that in the recursive algorithm, the only thing that is changing is the target. So we know that our DP has to cache the target. Now what did we do? Well, whenever we want to cache the target, we need to gradually fill it up from DP from the bottom up. So from the smallest value to the largest value. So we have this loop here in which we do that. And then what do? Well, then we have to go through the numbers and we have to figure out how many of them can actually form this target. So then we go through the individual numbers here. And what do? Well, we try to figure out, can this number, which is numbers at j, can this number form this target? And so if it can do that, then we update our DP array as such, and we basically just update it using this formula that we had here, target minus nums at I, target minus nums at j. And we could also maybe somehow improve this if we want. We could do for num in nums, and so then basically this nums at j would just be replaced by num. And so that is another way of doing the same exact thing. But I think I would just leave it at nums at j. Okay, so that's how you do this question. Thanks for watching.